Hello friends, today we will continue discussing the scattering theory. In the scattering theory, last time we discussed about the wave mechanical picture of scattering theory. We were discussing this, and using this wave mechanical picture, I told you that stationary wave function for scattering theory is this. I derived this equation just to recapitulate it, just to recall certain concept. Let me repeat something in this topic. Let us say now in wave mechanical picture we consider the incident particle as a plane wave. It is like plane wave, isn't it? It is an incident plane wave. An incident plane wave is represented by UINC is equal to EIKZ. Okay. Now at the scattering point, this is your scattering center. Scattering center, or you can say it is a target. Okay, and it has some potential V over certain range. Suppose up to this range there is a potential effect, and because of potential of this scattering center, this incident plane wave get scattered like this. It is scattered like this. Okay, and some of the incident particle may go ahead uninterrupted. Now this is the situation in case of wave mechanical picture. Incident plane wave, when it comes at the target or scattering center, at the scattering center, suppose it has some potential over some range. So in that range, incident waves comes. It gets scattered in all the direction. So now plane wave becomes the spherical waves. It becomes the spherical waves. Spherical waves. Okay, and that spherical wave is nothing but scattered wave, and that is f theta 5 into EIK R upon R. Now you see, I told you that incident plane wave is moving in this z direction, and that's why I have written EIKZ. But after the scattering, it becomes the spherical wave. So now instead of IKZ, I replace R with the R instead of Z. Why I have divided by R? Because the spherical wave, when it moves radially outward, that wave, scattered wave magnitude decreases with the radial distance. So as distance increases, scattered wave amplitude decreases. That's why I have divided by R. And what is this? This is nothing but scattering amplitude. Scattering amplitude. This coefficient is a scattering amplitude, and that is due to the scattering, and scattering is dependent on the nature of this target particle, or it depends on the potential V and its range. So whatever potential of target is there, the potential and its range, whether it extends up to this or that. So depending upon the range and strength of potential, waves scattered in all direction. So this represents the scattering amplitude. Okay. So now resultant wave, combination of this incident plus scattered wave becomes your waves at R. R is suppose very large. R is very large, means you are very far from the scattering center, and at that point the wave function u r at an infinite distance, where large distance r is nothing but u incident plus u scattered. It means u r at r tends to infinity becomes, u incident means it is eikz plus u as series f theta phi into eikr upon r. Okay. So up to this point we have discussed. Okay, and that wave is called the stationary wave function. This is nothing but a stationary. I said that it is a stationary wave function. Why it is called stationary? Stationary means if anything is steady, situation remains same over the time, then you can say it is a steady. Okay. So here I say that the incident plane waves are same over the time. Scattering center is the same. Then scattered wave function will also remain same. So mind well, I say that incident plane waves are steady, or incident particles are coming at the same rate. Flow is constant. Target is same. So the scattering will be same with the time. In that case, the wave function will also be stationary, that is independent of time. And that expression we can understand from this. And this is incident part, this is scattered part, and combination of this will give me the stationary wave function. This is, we have discussed it. But just to recapitulate it. Now let us say this is my stationary wave function. Then what I should do with this stationary wave function? What I can do? If I have a wave function, then how can I solve my wave function? I can solve my wave function with the help of Schrodinger equation. Okay? But since this is stationary wave function, it is independent of time, then I should also use the Schrodinger equation, which is time independent. So I am interested in writing time independent Schrodinger equation. Time independent Schrodinger equation. What is that equation? H cross square by 2m nebula square ur plus vr ur is equal to eur. This is my Schrodinger equation. This is a time independent Schrodinger equation. Okay? Stationary Schrodinger equation you can say, because my wave function is stationary. That's why I choose the stationary or time independent Schrodinger equation. Okay. Now if I want to solve this, I have to substitute that wave function in this Schrodinger equation, and I can solve that wave function. And I have to get the solution for this stationary wave function. So this is one approach, one method. So now this is one form of Schrodinger equation. Now I change its structure. How? I multiply with the minus 1 over here. Let us say it is a h cross square by 2m multiplied by minus 1 nebula square ur minus vrur is equal to minus eur. Isn't it? I just multiply by minus 1. Then I bring this over this side and this this side. So it is minus h cross by 2m lambda square ur plus eur is equal to another side vr ur. Now if I multiply this by 2m by h cross square, I multiply this equation by 2m by h cross square. So 2m by this will cancel out. So it's simply lambda square ur plus 2m e upon h cross square ur is equal to 2m vr upon h cross square ur. Now I define 2m e by h cross square as a k square and 2m vr upon h cross square as a ur. For this term I write k square, for this term I write ur. In that case it is lambda square ur plus k square ur is equal to ur. In another way it is lambda square plus k square ur is equal to ur. Now this is also the another form of Schrodinger equation, time independent Schrodinger equation. So now this is my Schrodinger equation, time independent. Then if this is my solution, I substitute over here and I solve it and I get the Schrodinger equation, stationary solution of the stationary wave function exact. Okay. Just to remind you, this is nothing but scattering amplitude. Solve. So now what we have to find out? We have to substitute this in this Schrodinger equation, and by some mathematical procedure you can get the solution of a stationary wave. This is one approach. So let me write down this expression over here. Just this is important one. This is the Schrodinger equation, time independent Schrodinger equation, ur and ur. Okay, and here you have to remember what is k square. K square is this, and what is u? That is over here. Okay. Now we have to solve this Schrodinger equation. You see, this is non-homogeneous equation, differential equation. This is the non-homogeneous equation. You should have idea that what is non-homogeneous and homogeneous equation. Just to get the idea, you have come across this formula. That is nebula square phi is equal to 0. Another formula I like this, nebula square v is equal to minus rho by epsilon 0. So when this is equal to 0, it is called the homogeneous equation. Homogeneous equation. It is homogeneous. But when this is equal to something, not 0, here in this particular case, suppose rho is the charge density. That is your source term, and it is not 0. So this is not equal to 0. Then that is, it is called the non-homogeneous equation. It is non-homogeneous equation. Okay. In that sense, this operator on this, it is not 0. It is not 0. Something is there like this. So it is a non-homogeneous. That's why I call it as a non-homogeneous differential equation. You know, this is your Laplace equation. This is your Laplace equation. So Laplace equation is homogeneous equation. And what is this equation? Poisson equation. Poisson's equation. Poisson's equation. Okay, and Poisson's equation is non-homogeneous. So now you should have an idea. Since differential operator operate on function, it is not zero. It is like this. So it is a non-homogeneous equation, isn't it? Now, one thing is that if you have a non-homogeneous differential equation, then instead of using this direct method to solve this problem, we have another method, and we will use that method, and it is called the green function method, isn't it? It is called the green function method. Now we will try to understand what is that green function method. Okay. Now in the green function method, suppose we have one equation like this. Just try to understand it. Have a patience and just try to understand. Suppose I have this equation. And it is like this. This is the operator, differential operator. This part is differential operator. This is UR, this is UR. FR, instead of FR, there is UR, UR. So, this is my non-homogeneous equation. So, this is also my non-homogeneous equation. This is my non-homogeneous equation. So, now what I am saying that non-homogeneous differential equation can be solved by the green function method. Now how? This is the general non-homogeneous equation. I will try to find out the solution of this non-homogeneous equation with the green function method. Then afterward we will use the same procedure for the time independent Schrodinger equation, which is non-homogeneous, and we will apply this method over here and we will get the solution. So first of all, our task is to understand the green function method. So now come to this point. First of all, now instead of solving this right at this point, just keep it aside. Try to understand the green function method. I told you that in case of green function method, suppose you have this non-homogeneous equation, let us say general non-homogeneous equation. How can you solve this? If you want to solve this non-homogeneous equation, you have to define the green function for that. Okay, so you have to define the green function. So we have to define the green function. Okay. First, define Green's function. GRR dash. Okay. We have to define green function first. So from this non-homogeneous equation, you have to define the green function first. How can you define green function? That is the problem, and that is the thing you have to understand. So now this is my differential operator. This operator should be the linear operator. So let this omega be any linear differential operator. This should be my linear differential operator. But here, what is the meaning of linear operator? In quantum mechanics, in undergraduate course, you have learned what is the linearity. Linearity means, it means C1 U1 plus C2 U2 is equal to C1 U1 plus C2 U2. If this operator satisfies this condition or follows this identity, then we can say it is a linear operator. So if omega be any linear operator, means it means it satisfies this thing. For arbitrary operator U1 U2 arbitrary waveform for U1 U2 function, you can say arbitrary function. Okay, so let omega be any operator which satisfy this identity of a U1 U2 arbitrary function and C1 C2 constant. Here what is C1 C2? It is constant. What is U1 U2? U1 U2 is the arbitrary function. Then linear combination is operated by some function, it will give this result, and that's why omega is called the linear differential operator. So first of all, this operator must be linear differential operator. It means satisfy this condition. Okay. Now, if this is the linear operator, then Green function, then any function G R dash such that omega R G R dash is equal to delta R minus R dash is said to be Green function for the operator okay. So just try to understand over here, if you have one general non-homogeneous equation and if you want to solve this equation, then you have to first define the green function. How can I define a green function? So if I have an operator which is linear operator satisfying this condition, then any function, green function G, such that it follows this condition, green function should follow this condition, is said to be green function for the operator. So G is called the green function if that function is, when operated by omega, it should give me the delta function. It is called the, this is, what is this? This is Dirac delta function. Okay, this is the Dirac delta function. So whenever I have to first define the green function, but how can I define green function? My function should be such that whenever I operate by the operator omega, it gives me the Dirac delta function as a result. If this is the case, then this is my green function. If suppose I write some function and operate on this, and if it is not delta function, then that is not my green function. So this is the condition that my function, any function, when operated by omega, it should give me the Dirac delta function. Then I can say yes, this is my green function. So if any function satisfies this function, if any function satisfying this condition, then this is a green function, otherwise not. So first of all, we have to define the green function, isn't it? So for any non-homogeneous equation, our problem is to write the green function. I can write green function in such a way that omega operated by green function must give me the Dirac delta function, and if it satisfies this condition, then it is my correct green function. So once I have green function, it's okay. Half work done. And suppose let us say we have defined the green function. Okay, we have for this non-homogeneous equation. Suppose I have defined the green function which satisfies this. Suppose. So now green function is ready for me. Then general solution of this. This is differential equation. Then general solution of this. General solution of this can be written. It can be written if this FR can be represented as linear combination of delta function. Means if you want to find out write down the general solution, you should have this function fr, and it can be expressed like this: delta r minus r dash fr dash into beta dash. Okay. As well as if u0r is any function such that omega u0r is equal to 0. If u0r function is such that omega u0 is 0, then the general solution can be written as ur is equal to ur0 plus grr dash fr dash into beta dash. Okay. Now just try to understand. It is heavy mathematics, I know, but there is no other way. So let us try to understand. For any non-homogeneous equation, first of all you have to define the green function. We have to define this function in such a way that it satisfies this condition. So if this satisfies this condition, then this is my acceptable green function. So now I have green function in my pocket. Okay. Then I can write the general solution of this. If I represent fr as a linear combination of a delta function, fr can be represented as a linear combination of a Dirac delta function. So now fr should be represented in this form. It should be represented in this form. As well as I have one function u0r such that omega ur0 is 0. I have chosen my wave function u0r, some arbitrary, is suppose omega u0 is 0, suppose. If this is my ur and it is such that when I operate with the omega u0, that is 0. Now if both these satisfied, then I can write the general solution for this non-homogeneous equation. Once again I repeat two lines. If whenever you have a non-homogeneous equation, you first define the green function using this property. This green function should satisfy this, and once it satisfies this, then it is your acceptable green function. Now you have green function. At the same time, this FR should be represented as a combination of a delta function, combination of a or integration with a delta function. So if I expand this FR term in this way, I have represented as a linear combination of the delta function. So if I can expand FR in this way, as well as this is 0, in that case this is my solution. Okay. So now this is my solution. Now I know my green function. So everything is known, and so that's it. That is your general solution for this non-homogeneous equation. If I apply same thing for this particular operator, instead of omega, suppose I have this FR, suppose I have this term. For this is non-homogeneous, what I will do? First define the green function, and same way this I represented as the expansion of this Derived delta function, and then I write down the general solution for this ur. So this is one approach. Now one thing you might not have understood that I want to clear first. You see, this is FR, this is delta function, but you know what is delta function? Any idea? What is Derived delta function? Let us try to understand what is Derived delta function. You have heard them of canonical delta, that is delta mn is equal to 1 for m equal to n is equal to 0 for m not equal to n, isn't it? Isn't it? Okay. Then Derived delta function, Derived delta function. Actually all these things you have learned in an undergraduate course. Derived delta function delta r minus r dash, and that equation that is equal to 0 for r not equal to r dash and equal to infinity for r equal to r dash. Okay, this is my Derived delta function. Now what is the use of this Derived delta function over here? So Derived delta function, okay, just try to understand. This is my Derived delta function. It is 0 at r not equal to r dash. Suppose I have, this is r, this is my r dash point, suppose. Okay. Now at this point r and r dash not equal, so my delta function 0. At this point r and r dash, because this is r, so r and r dash not equal mark, that's a 0. But when it comes over here, at that time r is equal to r dash, and my function will become, and then again r not equal to r dash, it is 0. So this is my properties of Derived delta function. This Derived delta function has a very important property. Very important. When I multiply any function with Derived delta function, any function with Derived delta function, what happens? It will give me the value at this particular point only. For other values, r not equal to r dash, it will be 0. So no need to get the integration. When r equal to r dash, it is there and you will get this. So just to explain you that Derived delta function has an important property. Whenever you multiply any function with Derived delta function, it will give the value of this at a particular point only. At what point? R is equal to R dash. So it will give the value at R only. And for other R, 0. Because delta R dash is equal to 0 for R not equal to R dash. So out of this integration, it will give the value at a particular point R equal to R dash. So this is important point. And this is how you can represent any function in this Derived delta notation, and then you can write this. Now again, you say that I have written down general solution with this expansion fr, this expansion, and with this condition. Let me repeat. I have solved this equation and general solution is this. Using fr is this and this condition. Using these two things, I have written down the general solution. But you may have a doubt that how can you write like this? So if this is my solution for this general equation, then when I put this solution in this equation, it should satisfy this. So whenever I take this general solution and I substitute over here, it should satisfy this equation. And next lecture I will try to show you that this general solution, when I substitute over here, it will satisfy this equation. And that's why this is my acceptable general solution for non-homogeneous equation. Okay. So for this solution, I require the green function. Okay. So now, next time I will show you that this is a general solution which satisfies this non-homogeneous equation. First thing. And secondly, I will use time independent showing the equation. Then I will use the same green function method and solve it. And it is easy method, but it is with heavy mathematics, so you should understand the concept of Derived delta function and all other things. Okay, I think you will work more and you will try to understand it. Okay, thank you.